Welcome to this presentation in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I'm David Beams. I'm an Associate Professor Emeritus of Electrical Engineering with the University of Texas at Tyler. This is a follow-on presentation to an earlier presentation about designing digital filters from analog prototypes using the bilinear transform. In that previous video, we designed first and second order filters, and I said we would do a follow-up presentation designing a complex digital filter. And that's what this presentation is about. So let's review the Cookbook method for designing digital filters using the bilinear transform. You begin with the kind and order of the filter that you want to implement. Then you decompose that filter into a series of second order sections for an even order filter, and you add a one or a single first order section for an odd order filter. You determine the frequency warped transfer functions of each of the sections of your filter. Then you determine the coefficients of the difference equation for each section of the digital filter using the equations that were developed in the preceding presentation. Let's do a real life example and see how this works. Let's do a fifth order 3 dB Chevy-Chev low-pass filter with a ripple channel ending at 100 Hertz. And just so we have an idea what we're looking for, I've calculated the frequency response of such a filter. And here's what characterizes it. 3 decibels gain ripple, 5 minima and maxima in the ripple channel, and the ripple channel ends at 100 Hertz. Now, why would we want to use a Chevy-Chev filter over another type of low-pass filter, like, say, a Butterworth maximally flat filter? Well, the advantage that the Chevy-Chev has compared to Butterworth is that the Chevy-Chev filter has a steeper transition from the pass band to the stop band than the same order Butterworth filter. The red trace here is the Chevy-Chev filter. The blue is the Butterworth, and you can see that the Chevy-Chev filter rolls off more quickly. But this comes at the cost of gain ripple in the pass band. Let's do the design. We'll start with the continuous time transfer function. And then using methods outlined in Sedron-Smith's text, we will determine the transfer function of a fifth order 3 decibel Chevy-Chev low pass filter with a ripple bandwidth of omega naught radians per second. Are you ready for this? Okay, there is the transfer function. Now the next step we need to do is we need to apply frequency warping. So let's assume a sampling period of 200 microseconds. And then this is the frequency warped value of the channel width. The unwarped value is 628.3 radians per second. The warped value is 629.15. In this particular instance, the warping has minimal effect. Now let's replace omega naught in the continuous time transfer function with its frequency warped value. And this is the continuous time transfer function after frequency warping that we are going to use as our prototype for implementation in digital form. We'll design each of the 3 sections in turn, starting with the first order section. Andiamo, which is Italian for let's go. I learned this from a tour guide in Milan in 2019. So here's the design of the first order section. Here is the transfer function of that first order section. Here is the general first order transfer function. And we can read the coefficients of the general first order transfer function from the specific transfer function. And now we calculate the coefficients alpha 1, alpha 0, beta 1, and beta 0 from relationships which were developed previously and are reproduced here. Here is the general first order difference equation. And here it is with numerical values. So we've got the first order section designed already. Let's go on to the second order section. Here is what I call section A. This is the transfer function. Here's the general second order transfer function. We can read coefficients off of the specific transfer function. And we get these values for the coefficients of the general transfer function. So far, so good. And we calculate coefficients alpha 2, alpha 1, and alpha 0. And then we calculate the coefficients beta 2, beta 1, and beta 0. And we have the difference equation. Let's put numerical values in it. And there we have the difference equation of second order section A. Now, transfer function of second order section B. Here again is the general second order transfer function. We read the coefficients. And in this case, it's just crank turning, plugging numbers in. We'll just jump right to the difference equation. And there it is. Okay. So we've actually done the design of this fifth order filter. We may not know it yet, but we've already done it. Okay, let's validate our work. Let's validate the design with Octave. Calculating the frequency response of our filter can be done using Octave's FREQZ function. Calculates the frequency response of a discrete time system. And it requires first that we find the equivalent fifth order difference equation. We can form the transfer function of the fifth order system by multiplying the three individual discrete time transfer functions and then reading the fifth order difference equation from their product. Octave can do this for us using its CONV or convolution function. We'll start by entering the coefficients of the difference equations for the first order section and second order section A. So here's numerator of the first order transfer function, which are the coefficients of the x terms. Here's the denominator of the first order transfer function. Here's numerator of the second order transfer function, and here's the denominator. Now what we're going to do here is we're going to multiply those two transfer functions to compute a third order transfer function by convolving the first order coefficients with the coefficients of the second order section. Then after we do that, we will come back and convolve this third order transfer function with the coefficients of second order section B to complete the fifth order difference equation. So here we have computation of the coefficients of the numerator of the third order transfer function. And here are the coefficients of the denominator of the third order transfer function. And now let's enter the coefficients of the difference equation of the remaining section, section B. There is the numerator of its transfer function. There's the denominator. And now let's find the coefficients of the fifth order difference equation by convolving the coefficients of this third order system with those of second order section B. There's the numerator. There is the denominator. So we now have the coefficients of the difference equation for the fifth order response. We're now in a position to validate our work. So let's create a range of logarithmically spaced frequencies from 1 Hertz to 1 kilohertz. Now let's calculate the corresponding angular arguments for use with FREQZ. And now, here we go. Let's do the analysis. Drum roll, please. It's just simple. This is the command to do the analysis to compute the frequency response. Now, H here comes back as a complex number. And for the moment, we're just going to be interested in the magnitude response. And we're interested in decibels. So let's compute the magnitude response in decibels. And then we'll put up a figure. We'll do a semi-log x plot where we have frequency plotted on a logarithmic x-axis and the gain in decibels on a linear axis. And we'll adjust the graph axes, and we will add X labels, Y labels, and a title. And now, let's see our result. Let's see, this is what we got from FREQZ. Let's see, if there are 5 min and max points within the ripple channel. We do have 3 decibels gain ripple. And the ripple channel does end at 100 Hertz. It looks like we have a fifth order 3dB Chebyshev response. But how does it compare to the analog prototype before frequency warping? Let's find out. Here I've plotted both the digital filter frequency response and its analog unwarped prototype, and you can see they're pretty close. If we compare the digital filter's performance to its unwarped analog filter prototype, I would say that we nailed it. So now, in principle, we can design digital filters of any length from their continuous time prototypes. Now, a small caveat, this is not the only way to design a digital filter. For example, probably the most direct way is to use what's called direct convolution, which requires that you have the time domain impulse response of the continuous time prototype. It's not the most efficient filter implementation, but it is a rather straightforward technique. And there are other techniques for designing digital filters as well. But for the moment, the real satisfaction in this design process, or frankly in any design process, is taking a concept and seeing it become reality. And frankly, for an engineer or a scientist, that kind of satisfaction is timeless. Thanks for exploring the world of electronics with us, and come see us in our next presentation.